So let's go through this example for Thevenin's theorem. I'm using the exact same circuit I explained Thevenin's theorem with. So here we have RL, and yes, we have to figure out the current I. So let's say the first step was to step one was first we have to replace the RL with open circuit. So basically what we want to do is figure out the equivalent circuit for this part, right? So we just keep that part and replace everything with just open circuit. All right, so let's do that. Okay, so step one, I have replaced the part RL with just open circuit, right? And we are interested in the voltage here because there is no current. So open circuit voltage, VOC, we are interested in this voltage. We have to figure out this voltage. So that is our step one. Step one, we have replaced it, and then step two basically is to, well, if you want to differentiate them between them, so we have to figure out the open circuit voltage, and for that you can use nodal analysis or basically anything you want. If you think using source transformation is useful, you can use that, and I think I might use source transformation here because it seems like I can use source transformation here, and then everything will become parallel to each other, so that would be much easier. But let's do it with nodal analysis, no problem. Okay, so this is our ground, and we have node 1 here. This is our node 2, and this is our node 3. Okay, so node 1, node 2, node 3. And if I actually write equation for them, well, first V1 equals to 32 volts. There is no confusion there. Then we have node 2. We have V2. Okay, let me write in white. V2 times 1 by 4 plus 1 by 12 plus 1 by 1, because those are the resistances connected to V2. I'm just doing nodal analysis here. Minus V1 by 4 minus 0 by 12 minus V3 by 1 minus V3 by 1, and then we have one current source, so minus 2 equals to 0. So this is our equation for node 2. And now for node 3. Well, okay, so node 3, I don't actually need to write any equation for that because I can tell that the node 3 will have the same voltage as node 2, because say if I had here 3 volt and I had here 5 volt, different voltages, then surely we will have some current, right? So we will have 5 minus 3 divided by 1 ohm. So we will have 2 ampere currents here. But we know that there is no current going through in this direction. Where will the current come from, right? So that's why the voltage must be the same on both nodes. So V2 and V3 will be same, okay? So when you have an open circuit like that, the current is basically 0, and then the voltage must be same, okay? So the voltage V2 and V3 are equal. So you can actually just replace it with V2, and you have V1 equals 32, so we can actually write it here, 32. And we can solve this equation to get the value of V2 or V3 to be something. Okay, let's calculate the whole thing. Okay, so we have V2 equals V3 here, and we are interested what the value of VOC is. Okay, so I should mention why are we doing this. Well, VOC equals to V3 minus 0, right? So, or in other words, V3 V2, VOC, they are all the same. Okay, so if we add up 1 by 4 plus 1 by 12 plus 1 by 1, we get V V2 times 12, 3 plus 1 plus 12, so we have 12 plus 4, that is 16, 16 by 12, so we have 4 divided by 3, so we have 4 by 3 here, minus 32 by 4 is 8, minus V2 by 1, so just V2 minus 2, and we have here V2 4 by 3 minus 1. I'm just taking common from these two terms. Then we have 8 and 2, so 8 plus 2 there, and then we have V2 4 minus 3 equals 10. Then we have V2 1 by 3 equals 10, and we have V equals 3 times 10, 30 volt. So we have the value of VOC to be V2 equals V3, which is just 30 volts. So when I said the value might be 30 volt, well, it was actually 30 volt. Okay, so we already know the value of VOC. And as you can remember from Thevenin's theorem, V Thevenin is equals to VOC. So we have V Thevenin to be 30 volt. So we have already solved one part of the puzzle, right? So this is 30 volt, and we don't still know the value of R Thevenin, but we have a formula for that as well, so nothing to be afraid of. Okay, so we have figured out some part of the puzzle at least. Okay, now it's time for step 3. For step 3, what we do is we replace the RL with short circuit. So this is what we got at the first. So we used to have open circuit here, now we have short circuit here, and now this time we are interested in the current, short circuit current, because short circuit voltage is very boring, that's just 0, right? And this is what we want to figure out. Well, again, we can use nodal analysis or Thevenin's theorem, whatever you like to, or source transformation or superposition, anything you want, any technique you want to calculate the ISC. Okay, so let's do that with just nodal analysis. We have V1 here, V2 here, and well, this whole thing is ground, right? So this whole thing is ground. So we have V1 equals to 32 volt, and then we have V2 1 by 4 plus 1 by 12 plus 1 by 1 minus V1 by 4 minus 0 by 12 minus 0 by 1, because 1 ohm is connected to ground as well, minus 2 for the 2 ampere current source that is entering equals 0. Okay, so we have V2 times, we have already calculated that to be 4 over 3 minus V1 by 4 minus 2 equals 0, and V1 is just 32, and 32 over 4 is 8, so almost same calculation, but this time we have V2 4 by 3 equals 8 plus 2, which is 10, and we have V2 equals 3 times 10 divided by 4. So this just equals to 15 over 2 or 7.5 volts. So V2, this voltage is 7.5 volt. Now how do we figure out the ISC, short circuit current? Well, the short circuit current is going through this, right? And well, the node here is, well, the whole node is 0 volt, right? The whole node here is 0 volt. So here we have 0 volt. So the short circuit current will be V2 minus 0. So short circuit will be V2 minus 0 divided by 1 ohm, right? And which is just again V2 happens to be 7.5. So we have I short circuit equals to 7, okay, let me write it again, V2 minus 0 by 1 ohm here, so 7.5 minus 0 divided by 1, which is just 7.5 amperes. So we know the short circuit current now, And if you remember, the formula for Thevenin's resistance is just VOC divided by ISC, right? And what our VOC was? Well, from step 3 we have, step 2 we have VOC to be 30 volt. Okay, so we have 30 volts. So our VOC is 30 volts and ISC is 7.5 amperes. And voltage divided by ampere is, of course, current. So voltage divided by current is, of course, resistance. And we have 30 divided by 7.5, just 4 ohm. So when I said I was talking about our Thevenin to be 4 ohm, well, that wasn't an accident either. You can find our Thevenin to be 4 ohm. So now you have learned that the whole thing is just equivalent to a 30 volt voltage source and a 4 ohm resistor. And anything you want to know about the main circuit, you can answer it from this circuit. Okay, so that's the benefit of Thevenin's theorem. Okay, so this is one way. I will show you an example, but before that I want to emphasize on why this is important. So for example, think about all the circuits you can imagine, right? So the whole electrical system in Bangladesh, the whole electrical grid is just one huge circuit, right? Probably at least from anywhere the circuit is connected from grid. So maybe the Kaptai power plant is generating power from somehow generating power from here. Then it's going from tower to tower to transformers and whatnot, and then going to different houses and whatnot. So all the circuits in your, all the powers connected in your circuits, all the wires in your home is actually connected to say Kaptai electric power plant somehow. All right, so the whole Bangladesh system is a huge circuit, and you can imagine there will be millions and millions of nodes, right? And no one will ever dare to use nodal analysis there. But using Thevenin's equivalent circuit, Thevenin's theorem, you can basically transform the whole thing into just a simple voltage source and resistance. Okay, so maybe you have a wall plug, okay, and you stick don't try this at home. You can stick a multimeter into the ports, and you see the voltage is around 220. So maybe the voltage in your house is 220. So you have this multi-plug, so this plug in your house, and you use a multimeter probe here, and multimeter probe here, and the multimeter shows you that you have 218 volt. Okay, so this is your open circuit, because if nothing's connected, this is open circuit. So this is your Thevenin's voltage. And now, which is a little risky, you can actually short circuit. Well, of course your home's power switch will pop. Okay, so your circuit breaker will pop. But if you can connect and measure the current using multimeter, so that's why I'm saying don't try this at home. Maybe you say, okay, the current here is maybe 5 amperes, let's say. Then you have this is your short circuit current, because you have short circuited, and this is the current you get, and so your R Thevenin will be 218 divided by 5 ampere, 218 volt divided by 5 ampere, and whatever that is. The beauty of this is that you don't have to go through all the circuits in the whole Bangladesh, or anything actually. You just can calculate using just tools in your home, basically, to calculate all the effect of the whole circuit. So the whole Bangladesh system's circuit is going to be converted into just one voltage source, so 218 volt, and whatever this value is, maybe it's 53.6 ohms. So maybe I think that's correct, I don't know. So just one resistor, 43.6 ohm, and this is the whole equivalent system for the Bangladesh system, Bangladesh electrical grid system. Okay, so that's how powerful Thevenin is. But this is mainly what Thevenin's theorem is really. So this is very powerful and very useful, and we always use this. Okay, so that's it.